Hello everyone, I am Bhagresh Mishra, a PhD student at IIT Bombay, and this is week 10 of Biophotonics course. So, in this course, in this week, uh, optical tweezers, optical scissors, or laser tweezers, laser scissors, laser drilling has been discussed in the lecture. So here in this live interactive session, I'll just discuss the assignment questions for the week 10. Okay, so the first question is, optical tweezing action is based on A. Forces arising from the change in energy of photons, B. Forces arising from the change in momentum of light, C. Both change in energy and momentum of light causes tweezing action, and D. None of these. So the correct answer is B. Forces arising from the change in momentum of light, because so basically you need force in order to trap or tweeze the tissues, okay, in inside in the from the bunch of tissues or cells. Okay, so that force comes from the change in momentum of light means the laser light. So depending upon the uh, with laser lights, with laser you can make the forces very large enough to accelerate, deaccelerate, deflect, guide, and trap the small particles. So that small particle is in nanometer uh, to micrometer size. Okay, so uh, let's discuss a little bit about optical tweezing or optical trapping. So so this content I have taken from the this introduction to biophotonics books by Prasad. So optical trapping is based on the fact that photons have linear momentum. So the whole idea is to utilize the linear moment change in the linear momentum of the photon in a certain time, which produces the force. Okay, so suppose I have a spherical particle with refractive index greater than the surrounding medium, in which laser beam with a wavelength lambda, which is much smaller than the radius of the particle. Okay, so in this case uh, the linear momentum, so uh, optical trapping is based on the fact that photons have linear momentum. This momentum changes when a photon changes direction, as when crossing an interface between two media of different refractive index. Okay, so uh, since the total momentum is conserved, so the difference between initial and final momentum of a photon transferred to the particle, uh, and that photon is responsible for the force appear on the cell, on the sphere. Okay, so that is, sorry, that is that force is delta p by delta t, where p is the momentum and t is the time. Okay, the change in delta p is change in the momentum and delta t is change in the time. uh, Now so you have seen this diagram uh, in the lecture video, that suppose I have a spherical, oops, suppose I have a spherical particle. Okay, so two photons are coming from each side. Suppose this one is this is AB, and this one is capital A, capital B. So here two photons, and here one photon. So obviously force exerted by this capital A, capital B photon is, capital A, capital B photons are greater than the small a, small b photons. Okay, so then there will be some kind of refraction happens. So and then again transmission like this. Similarly here, and then again, so they make this X kind of structure, X kind of shape. So this so the resultant vector is here. The resultant force exerted by this one photon on this sphere is in this direction. PQ, and for this the resultant force is in this direction. This is capital P, capital Q. Please note that here we need two forces, okay, uh, to control the motion of the sphere. Okay, if you have one force, then you won't be able to get much control. Okay, or you won't be able to trap the cell that much, like you need basically two forces in order to give direction. Okay, with the one force you can only push in one direction. Okay, and then if you want to push the cell into another direction, you need to apply the force from that direction. Okay, so rather than that, you can have the two forces, then you can control by just manipulating the intensity uh, of the of the of the light. Intensity means in a particular time more number of photons are going inside the cell or inside the sphere. Okay, so you need two forces. uh, so from there you can have the gradient force. Okay, the resultant gradient force, which will be so this is uh, p small sorry small p and small q, and then you have a bigger force in this direction. Okay, and this is capital P, capital Q. So of course this one is bigger, so the resultant gradient will be in this direction. So this is resultant gradient force. So from this you can control the motion of the sphere. Okay, so if you want to move it along this direction, then you should have more number of photons. That means pq should be greater than the small pq should be greater than the capital pq. Or if you want to move this in this direction, then you should have more number of photons in this capital P capital Q direction, or you can say the force. Okay, so by this way you can trap the sphere, and accordingly you can move it. Okay, now but these are not the only thing. Now what should be the value of this gradient force? I mean, it's like you are inserting the gradient forces, but it is still not moving. Okay, because there may be some reflection happening at the interface. Okay, so in order to have less reflection at the surface, because there will be some scattering by this cell of the scattering of the laser light by this sphere. Okay, so and that will cause the reflection. So to reduce the reflection, the particles should be suspended in a liquid such as water, not in air, so that the difference between the refractive index of the particle and the surrounding should be lesser the difference between the index, lesser will be the scattering, and thus lesser will be the reflection. Okay, so in order to move or trap the sphere, the cell or tissue, you should have the gradient force greater than the scattering force. That is why you should put sample in water or in any liquid which has refractive index comparable to the refractive index of the cell. Okay, and this trapping is also based on the size. Okay, there are different type of trapping. Okay, so as per the so according to the size of the particle compared to the wavelength, different models of trapping interactions are used. So when you have a radius much less than lambda, then you need to use Rayleigh model for radius slightly less than the wavelength. You can use the electromagnetic model, and for radius greater than lambda, which is the case here we are discussing, you need to use ray optics. Okay, like so r greater than lambda, which is the case for biological cells. Biological cells, you need to use ray optics. Okay, you need to use ray optics. So yeah, so these are the things. So the resultant gradient force should be greater than the scattering force in order to trap or tweeze the cell. Okay, So let's go to the second question. mm, Pick the incorrect statement. So number A, optical tweezers are non-invasive method of manipulation. B, near IR laser beams can manipulate the cells without damaging them. So C, in scissoring action, light must simply pass through and the molecules must not absorb the light. The force exerted by optical tweezers is so weak that it cannot manipulate group of tissues. So as you can see, the option A is correct. It is optical tweezing is a non-invasive method of manipulation. B is also true. Near IR laser beams can manipulate the cells without damaging them. In order to manipulate means in order to trap or tweeze, you need near IR lasers, which should not be absorbed by the tissues. Okay. The third one, in scissoring action, light must simply pass through and the molecules must not absorb the light. This is incorrect statement, because for the scissoring action you need molecules to absorb the incident light. Okay, the transparency should be for the optical tweezing action, not for the scissoring. Okay, so for scissoring you need molecules to absorb the laser light. So the correct answer is C. Okay. And yeah, the force exerted by optical tweezers is so big that it cannot manipulate group of tissue. This is also correct, because with the help of optical tweezing action you can manipulate one single tissue or one single cell, not the entire group. Okay. So let's discuss a little bit about this scissoring action. Okay. So the laser scissor action utilizes photoablation by a pulsed UV laser. A suitable UV laser so a suitable UV laser is pulsed nitrogen laser that provides 3 nanosecond pulse output of energy 120 to 300 microjoule at 337 nanometer wavelength. Okay, so when focused through a high numerical aperture objective, it can produce a high photon density in a spot that is less than 1 micrometer. So the spot should be very less, and that the spot should be circular. Okay, so that it cannot damage the neighboring cells, and also the size should be comparable to the size of the cells. so that it cannot destroy the healthy cells or healthy tissues. Okay. uh, this high photon density of UV radiation produces photoablation by the photochemical decomposition of cellular or tissue structures. And this uh, so in this process the laser scissor can cut a spot size less than 1 micrometer, okay, without damaging the neighboring cellular structures. And so this laser beam can be introduced using inverted microscopy. Okay, so using this process, the laser scissor can cut a spot size less than 1 micrometer without damaging the neighboring structures. Okay, so this is the process of the laser scissoring. So here the important thing is the spot size. Depending upon the size of tissue, the spot size should be modified, or accordingly laser should be used so that it cannot destroy the neighboring structure. Question 3. The property of light that controls the overall movement of the particle in laser tweezing process is wavelength of light, frequency of light, duration of laser pulse, intensity of light. So for the optical tweezing, as we discussed, higher the number of photons, higher the forces. Okay, so number of photons is nothing but, I mean, in a certain time interval, is nothing but the intensity of light. Okay, so the correct option is D, intensity of light. So with lasers one can make forces used for optical tweezing large enough to accelerate, deaccelerate, deflect, guide, and trap small particles. This is a direct consequence of the high intensities and high intensity gradients achievable with continuous wave coherent light beams. Okay, so clearly it is the intensity, high intensity and high intensity gradients, not the other things, wavelength, frequency, duration of laser pulse. So it's all about intensity, which gives the change in momentum, which gives the force to trap or twist the particles. Okay, so question number 4: which of the following conditions ensure that the particle is trapped by a laser beam? So let's draw a diagram, force diagram for a particle. So suppose I have a particle here. Okay, so on this particle it is suspended in a liquid. Okay, and you have a beam somewhere, like beam axis is like this. So this is beam axis. So uh, so if beam axis is in this direction, then you have the scattering forces in upward direction. So scattering is happening in this direction, and since it is suspended, there will be some gravity, f of gravity, and also some buoyancy force, f of buoyant, and the gradient is in this direction. So in order to trap the particle by this gradient force, the F gradient should be greater than the F scattering, and this buoyancy force should equal with the gravity force. Okay, F buoyancy should equal to the F gravity. So the right answer is option D. Okay, fifth question: optical tweezing action requires lasers that have a single transverse output mode because uh, uh, to make sure there is an existing electric field component in the direction of propagation, to make sure there are no existing electric and magnetic field components present in the direction of propagation that can disturb the molecular structure of nanoparticle. This is the correct statement. To make sure there is an existing magnetic field component in the direction of propagation, this is also not true. To make sure that unwanted noise is not present that can affect the trapping action, this is also true. To give rise to a change in momentum of photon, this is not true because change in momentum is due to intensity of the laser, and to focus the optical beam to a single very small spot. And this is also true. Okay, so B, D, F are the right options. Now, so let's discuss little bit about this single transverse output mode. Single transverse output mode. Okay, this is also known as TEM00 mode. Okay, so first let us discuss transverse output mode. Okay, or what is the transverse mode? So the distribution of light confined within an optical resonator is described by spatial patterns called transverse modes. Okay, it is represented as TEM with subscript NM. So T for transverse, EM electromagnetic, and NM is the important thing here. So this N and M refer to the number of intensity nodes of the resonator mode pattern along X and Y axis. Okay, so now so the TEM, so for this case it is single transverse output mode, which is the TEM 00 mode. So it is the lowest order transverse mode. It has the lowest threshold, smallest beam width, and divergence, and contains no nodes in the output beam transverse intensity distribution. Okay, so this TM00 mode, it has the smallest beam width, smallest divergence, lowest threshold. So the main important thing is this smallest beam width and divergence, so that you can get a very small spot. So if you, so the spot made by this This TM00 mode is like this. uh, so this is the spot, and if I so it's like this. Okay, it's the a single spot. This is uh, TM00. Just for example, uh, TM11. So if you have a TM11, then you have these spots. So this is TM11. So okay, so you don't require these kind of spots or divergence, because it will not give you the proper spot, proper position, and also it diverges and will have some noise. So that is why TM00 is used for the optical twitching action. Okay, so next question. Statement 1. The power and wavelength of a laser determine how well a particular microscope objective can focus the laser. Statement 2. A laser power between 20 and 100 milliwatt at the microscope is sufficient to carry out trapping experiments. So the correct option is statement D, option D, which says statement 1 is incorrect and 2 is correct. So basically, for uh, for such kind of experiments, you need a microscope with a high numerical aperture objective lens to focus the laser, and also a continuous wave laser source that provides wavelengths at which biological samples are transparent. So generally, near visible region is used. Okay, that means 700, like visible to near IR, or you can say near IR, basically not visible, because visible is still 400 to 700. So 700 to 1300 nanometer range is used for optical trapping, because it doesn't get absorbed by the cells. Okay, so question 7. Why is no heat generated in the cold ablation process? So cold ablation process occurs in the laser scissor action. Basically, this is the photo ablation. So this is like we have discussed the thermal relaxation time in the previous lecture. So thermal relaxation time tells how quickly or slowly an object loses its heat. So basically, it's how quickly it cools. Okay, so that is why the correct answer is option B. The thermal relaxation time of the cellular components is higher than the pulse duration of UV laser. That is why there is no heat generated in the cold ablation process. Okay, so or very little heat is generated. The parameters that help in controlling the depth of the optical drilling are intensity of laser, power of laser, time of focusing the laser, all of these. So the correct option is all of this, because you need all these three: intensity, power and time for the optical drilling. Okay, intensity and power will give you the force to make a hole in the tissue, and time of focusing the laser will give you the depth till which you can drill in the tissue. So all these three components are required for the to control the depth of the optical drilling. Okay, which of the following is used in the laser pressure catapulting process? So the laser pressure catapulting process, nitrogen laser is used. So what is laser pressure catapulting process? So first let's discuss. It is basically the micro dissection. So what is micro dissection? uh, Laser micro dissection is to excise a single cell or pure cell population from a tissue. Okay, so now let's discuss about the laser pressure catapulting process. So in this process, uh, so in first step, nitrogen laser beam is used for micro dissection. Okay, once the cell is dissected, the same laser with approximately twice the energy level is focused from below the tissue. So depending upon the size of the excised sample, one or a few laser shots produce enough laser pressure force due to the extremely high photon density of the focused beam to catapult or eject the sample into a collector cap. Okay, so this is the process of a laser pressure catapulting, which uses nitrogen laser to catapult the tissue. Okay, so now the last question is, which of the following are applications of laser scissors? Opto injection. So here we are injecting something, that means first we are drilling or making a passage to inject some drugs or whatever. So of course yes, A is the application of laser scissor. B, trapping cell organelles. Trapping is the application of optical tweezing or laser tweezing, not the laser scissor. C, microsurgery. Yes, of course, because it again requires some kind of drilling. Micro dissection, which we just discussed this is also true. Tweezing of organic nanoparticles, I mean again this is the application of optical or laser tweezer or yeah, laser tweezer. And the F, optical drilling, this is also application of laser scissor, because you drill in the tissue by laser scissor. Okay, so yeah, um, this is done for this week. So I have discussed all the assignment questions here. We will meet in the next class and next Friday. So okay, bye bye.